radical and exponent rules. So just to start off, we're going to talk a little bit about radical form and exponential form. Using variables to represent each piece. The radical is drawn in pink. The radicand is what's underneath the radical sign. My exponent is in green, and my index is in blue. Now, if you're taking the square root, there'll be nothing written here, but the smallest index that you can have is a 2. This is radical form. When changing it to write it in exponential form, the radicand is basically the base. E is the exponent, it's the numerator of the fractional exponent. And n, the index, is the denominator of the fractional exponent. Given that you have a radical where b is the radicand and n is the index, when b is a real number and n is a positive integer, if n is odd, there's only one real root, and if n is even, and b is positive, so we're not talking imaginary numbers, then there are 2 real roots. Now this makes sense because if n is odd, that's like saying the cubed root of 8. There is only one real root there, and it's a 2. However, if n is even, that's like saying the square root of 4, which we know can be positive or negative 2. The principal root is the positive 2, and the negative or the opposite root is the negative 2. Now we know that if you see a question where it's already has the square root symbol drawn, it's only looking for the principal root. But if I have an equation where I'm solving and I draw the square root on both sides, it's looking for the principal root and the opposite root. For any real number a, where a is the radicand, if we're looking at the exponent and the index, once we get the exponent and the index to match, it's true that the answer, a, will just be a if n is an odd number. So just like we talked about, if it's a cubed root, there's only one answer. But it's going to be the absolute value of a if n is even. Now the reason for this is we're not talking about the negative or the opposite root because the square root symbol is already drawn. Now when it's numerical, it's easy. But when it starts working with variables, that's when you have to remember that you need to draw the absolute value symbols. So if we have the cubed root of 8, like we had in the last slide, the cubed root of 8 is 2, because 2 times 2 times 2 is 8. You can't have a negative 2, because that would give you a negative 8. The square root of 16, we're talking that it is just 4, because the square root symbol is already drawn. So here, we could think of the cubed root of 8 as being the cubed root of 2 to the third. The 3 exponent and the cubed root essentially cancel out, leaving me with a 2. Here, we can think of it as the square root, the 2 we don't have to write, but just to visualize it, and this is 4 to the second power. Again, essentially, this is canceling and this is canceling, and what we're left with is the absolute value of this answer, which is a 4. Now, when you work with variables, this is where you really need to remember the absolute value. We need to rewrite this so that the whole thing is being talked about to the 4th power. So we need the index and the exponent to match so that it's easier to write our answer simplified. So 16 is the same thing as saying 2 to the 4th. And a to the 5th is the same thing as saying a to the 1st to the 4th power, because when you raise a power to a power, you multiply the exponents. So this would then mean that the radical and the exponent would cancel, and since it's an even, our final answer that we'd be left with is the absolute value of 2a, because we're only taking the positive root, the principal root. Now in our next example, we're going to be taking the cubed root, which means we want this whole thing to be raised to the 3rd power. Now 27 is the same thing as saying 3 to the 3rd power. And a to the 12th is the same thing as saying a to the 4th to the 3rd power. Again, the radical and 3 is the index is canceling with the 3 as the exponent. But since it's an odd number, our final answer is just 3a to the 4th. We don't need the absolute value symbols.